Hello there, ATS EVS 105 students. This is Dr. Shragi, and we're starting Module 6 now, which is a set of topics that come from Chapters 6 and 7 from the first edition of the textbook. And we're going to be starting today by talking about radiative forcing, but, well, actually, first we kind of have to get another concept together about time lags in the climate system, how it takes time for changes to happen in the climate system. I like the analogy your textbook talks about. It says, if you stick a cold turkey into the oven that's already heated up, it doesn't immediately become hot and cooked. It takes time. There is a certain amount of time it takes for the turkey to reach the temperature inside the oven. And the time lag between putting the turkey into the oven and the actually turkey being up to full temperature is a manifestation of what we call the turkey's thermal inertia. Thermal inertia is a term that physicists kind of hate. It's not a very scientific term. If I had to just cut and paste a definition I found on Google, when I just typed in define thermal inertia, it says the degree of slowness with which the temperature of a body approaches that of its surroundings, which is dependent on its absorptivity, its specific heat, its thermal conductivity, its dimensions, and other factors. See, physicists would be unhappy with this word thermal inertia because they'd want to know about all those other factors. But this basic idea that there is a period of time, a lag between when something, when there's a difference in the temperature between two parts of a system and when they come back into balance is called thermal inertia. And in the same sort of way, the temperature of the Earth doesn't instantaneously respond to additions of greenhouse gases in the Earth's atmosphere, which can be hard to picture. I mean, if the Earth were in a perfect energy balance where there was a certain amount of energy in from the sun, which we'll label E in, and a certain amount of energy out in the form of long-wave radiation, E out, if they were in perfect balance, well, it's not so hard to picture how this would work. E out would have to be determined by the temperature of the object. That's Stefan Boltzmann's law, right? The amount of radiation that's going out depends on the temperature of the object doing the emitting. So, okay, these two things would be in balance. E in would be in balance with E out, and E out would be determined by the temperature. But what if there wasn't a balance? What if there was more energy in than energy out at the present time? Well, that would mean that there would be more energy in than energy out. It means we have a net heating of the surface, which is going to adjust the temperature of the surface, make the temperature of the surface warmer and warmer, which by Stefan Boltzmann's law means that it will emit more radiation until E out matches E in again. But that takes time. It doesn't immediately, the temperature is increasing, but it has not yet gotten to where it needs to end up. So, for example, in the present climate system, the Earth isn't quite in energy balance. Your textbook uses the number of being off, that the energy balance is off by about 0.9 watts per square meter. That slide that we used in the energy balance lecture that came from NASA used the number of 0.6. Those are both pretty good estimates in my mind of what the current energy imbalance is. In other words, every square meter of the Earth is currently warming at a rate of somewhere between 0.6 and 0.9 watts per square meter. And there is some new temperature that the surface of the Earth overall will need to reach in order to achieve energy balance again. There will be some new temperature that the Earth has to reach for the energy out, as dictated by the Stefan Boltzmann law, is now balanced by the energy in that comes from the sun and greenhouse gases and so on. But here's the deal. At this rate of warming of just, a fraction of 1 watt per square meter, it's going to take decades to reach that new temperature. Even if we stop adding greenhouse gases now, those greenhouse gases are already in the atmosphere, creating the warming, and the warming is slowly stepping the temperature up, but getting to that new final temperature is going to take decades, and there's nothing we can do about it. In fact, there's a great vocabulary word to describe that: committed warming. Committed warming is warming that it's already coming. We can't do anything really to stop it because those greenhouse gases are already in the atmosphere. It's just that we have not yet gotten to the temperature that will achieve the new energy balance. This is a real problem for the whole business of climate change and climate policy and so on, because in order to make changes, any change we make today and pay for today, like improving public transportation or investments in wind and solar and things like that, the benefit from that won't come for decades, right? That's warming that won't happen, but not today, not next year, decades from now. That's a real policy problem. Voters hate making sacrifices now for something that they won't see benefits for decades to come. This idea of an imbalance between the energy in and the energy out of a system and the time it takes to get them back into balance leads to an important notion that is the main theme of today's lecture, and that is radiative forcing. But before we get into radiative forcing, let's just do a couple quick questions about what we just saw. Question 1. Because of the thermal inertia of the Earth, if the Earth is not in energy balance at the present time, A, the global mean temperature cannot change, B, the carbon cycle will be modified until a new energy balance is achieved, C, the temperature will instantaneously increase so that a new energy balance is achieved, or D, the temperature will increase over a period of decades until a new energy balance is achieved. Which of those is the correct explanation of what the Earth not being in a energy balance and having thermal inertia? Alright, choose from one of those 4 options, get a little feedback before you move on to question 2.